So when we consider pure water is going to be only H2O. As it turns out, pure water can actually react with itself, where one of the waters will behave like an acid, another water will behave as a base. Remember, an acid is a proton donor, a base is a proton acceptor. Notice how this particular water is going to end up becoming OH negative, which is hydroxide, because it loses a hydrogen. This water will end up becoming H3O plus, which is hydronium. And this happens in pure water. Now, this happens to a very, very small extent. If you have pure water, it's mostly going to be water, but some of it will become hydronium and hydroxide. Now, we can actually set up an equilibrium expression for this and figure out the K value for this. And if you remember, the K equilibrium expression is products over reactants. But something to keep in mind is that it's the aqueous products divided by the aqueous reactants. Notice how these are aqueous, but these are liquid. And so the reactants are not included in the equilibrium expression because they are liquid. So when you set up a equilibrium expression, it ends up being this. And we have determined that Kw for water, for the equilibrium expression for water, the equilibrium constant for water, is 1 times 10 to the negative 14. These two pieces of information we're going to use to help us calculate these problems, these next problems. Now, something to keep in mind is these multiplied together will always equal 1 times 10 to the negative 14. So if we were to increase the hydrogen ion concentration of water by adding an acid to the water, for this expression to be true, you have to also decrease the hydroxide ion. So again, if you add acid to pure water, you'll end up increasing the hydrogen ion concentration, and to compensate for that, you'll end up decreasing the hydroxide. Again, these two values here always multiplied together, or these two values multiplied together will always give us 1 times 10 to the negative 14. So if we have an acidic solution means that we're going to end up having a greater amount of hydronium ion. A basic solution is going to end up having a greater amount of hydroxide ion solution. And if it's a neutral solution, that means we have equal amounts of hydronium and hydroxide. Now, when we're looking at this next problem, we're going to use this information here that I've circled and squared to help us solve this next problem here. This next problem is saying that we are taking this many grams of sodium hydroxide, which is a strong base. What that means is that 100% of it will dissociate when added to solution. And it's added to distilled water. That's a volume of this. So what we can do is we can take the grams and we can convert the grams into moles, and we can figure out how many moles per liter there are. So the first thing we need to think about, though, is what is sodium hydroxide? Well, sodium has a 1 plus charge, hydroxide has a 1 minus, and so we end up with sodium and hydroxide. Sodium hydroxide, when put in solution, will give us this plus this. Now, something we need to keep in mind is this 4 grams, or 0.4 grams of sodium hydroxide, we we need to figure out how many moles that is. So we're going to go from grams to moles. For every 1 mole, there's 39.997 grams. And if we type that into our calculator, we end up with 0.010 moles. Now remember, because it's a strong base, that means that whatever amount of sodium hydroxide we have, 100% of it will go in this direction. And for every one of these, we're going to end up producing one of those. So that means if we have 0.010 moles of this, we're going to end up producing 0.010 moles of this in solution. Now, this many moles are put inside of 1 liter. And so to find the concentration, we just take our moles and we divide it by our liters, which happens to be 1 liter. And that's going to, again, give us 0.010 moles, molar solution of hydroxide. So this is going to be the concentration of the hydroxide, which happens to be the answer for number 2. Number 2 is asking for us to calculate the hydroxide ion concentration, which happens to be this right there. Now, for number 1, though, to calculate the hydronium ion concentration, we need to use our equation that we just learned, which is Kw is equal to the hydronium ion concentration multiplied by the hydroxide ion concentration. And we also need to keep in mind that Kw is 1 times 10 to the negative 14. So let's go ahead and plug this in now. So we're going to take this equation here and plug in what we know. Well, we know what Kw is. We are looking for the hydrogen ion concentration. And we just calculated our our hydroxide ion concentration, which we just plug into here. And now all we need to do is solve for the hydrogen ion concentration by dividing. We get 1 times 10 to the negative 12 as our answer. So just to recap real quick, we knew how many grams of sodium hydroxide we put inside of 1 liter. We converted the grams to moles. We know what 0.010 mole goes into 1 liter, so we can get our molarity for the hydroxide ion concentration right there, which is the answer to number 2. We then take that value and we plug it into our Kw expression there to get the hydrogen ion concentration. Now, number 3 is asking if the solution is acidic or basic. And there's really 2 ways of knowing. First off, what are we putting in the solution? We're putting a base in the solution, so it was going to be basic. Secondly, we can tell by looking at the concentration of the hydroxide. If you take a look, the concentration of the hydroxide is 0.010. The concentration of the hydronium is 1 times 10 to the negative 12. There's a greater concentration of hydroxide, and according to this right here, greater concentration of hydroxide means that it's going to be basic. Alright, for this next problem, we're going to look at a 1.5 times 10 to the negative 4 molar solution of calcium hydroxide. Now, this is already giving us the molarity of the calcium hydroxide, but something we need to keep in mind is that if we have calcium hydroxide, when it dissociates into solution, it's going to create 1 calcium ion plus 2 hydroxide ions. Because if you take a look, there's 2 hydroxide ions right there. So when considering that we have a concentration of calcium hydroxide of 1.5 times 10 to the negative 4, and we know that for every one of these, we're going to produce twice as many hydroxide ions. All we need to do is take this right here and multiply it by 2. to figure out the concentration of hydroxide. And again, the reason why is because for every 1 calcium hydroxide, we're going to produce 2 hydroxides. So when we double that concentration, we end up with 3 times 10 to the negative 4 molar solution of hydroxide. We can now take our concentration of hydroxide and we can use our equilibrium expression for water. And we can take this, plug it into here, and we can then use that to calculate our hydrogen ion concentration. And there we have it. Keep in mind that Kw will always be this value. And notice how I'm writing it as H plus rather than the H3O plus. The reason why I'm doing that on purpose, is so that you understand that they're the same thing. If we solve for the hydrogen ion concentration, we end up with 1 times 10 to the negative 14 divided by 3 times 10 to the negative 4. And that will give us 3.3 times 10 to the negative 11. And this is the answer to number 4. Now for number 6, is it acidic or basic? Well, again, what are we putting in the solution? We're putting a strong base in the solution. We're putting a base in the solution. So it's going to be basic. But just looking at the hydrogen ion concentration versus the hydroxide ion concentration, we have a greater concentration of hydroxide, which means it's going to be basic. Now here's the answers for 7, 8, and 9. Feel free to give it a shot. Again, the answer key is going to be on my website for the practice problems that are after this. If you have any questions, feel free to email me. Have a great day.